What if everything we know about time is only half the story? Picture the universe not as a straight line stretching endlessly forward, but as an intricate, rhythmic dance, a vast celestial clockwork where events repeat in perfect, mesmerizing cycles. This idea isn't just science fiction. Ancient cultures from the Mayans to the Babylonians built entire civilizations around the belief that cosmic patterns repeat, like the hands of a clock returning to the same position. And today, cutting-edge astrophysics is uncovering startling evidence that they might have been onto something profound. Think about the way seasons come and go, or how the moon waxes and wanes in an unbroken loop. These aren't just random occurrences, they're glimpses of a deeper order, a hidden rhythm woven into the fabric of reality itself. Scientists now suspect that everything from the orbits of planets to the birth and death of stars might follow grand, repeating cycles, almost as if the universe is ticking like some unimaginably vast timepiece. But here's the real mystery. If these cycles exist on such a colossal scale, what does that mean for our understanding of time, space, and even our place in the cosmos? That's exactly what we're about to explore. Over the course of this journey, we'll travel from the observations of ancient sky watchers to the latest breakthroughs in quantum physics, piecing together the astonishing possibility that the universe operates like an endless, self-regulating machine. We'll see how black holes, galactic formations, and even the expansion of space itself might all be part of this grand celestial clockwork, a hidden order that could rewrite everything we thought we knew. So settle in, because by the end of this video, you might never look at the night sky the same way again. The cosmos is calling, and its secrets are more rhythmic, more mysterious, and more breathtaking than we ever imagined. The idea of celestial clockworks suggests the universe operates like an enormous, precision-engineered mechanism where cosmic events don't just happen, but recur in intricate, repeating patterns. Imagine a pocket watch, its gears turning in perfect sync, marking the hours without fail, now scale that up to galactic proportions. This isn't just poetic imagery, it's a framework that connects the dots between ancient stargazers and today's astrophysicists, revealing a universe far more rhythmic than we ever realized. Take the ancient Babylonians, for example. They meticulously tracked the movements of planets, predicting eclipses and planetary alignments with astonishing accuracy. They didn't see time as a straight line but as a series of returning cycles, a belief echoed by the Mayans, whose long count calendar revolved around vast cosmic periods repeating every 26,000 years. These cultures weren't just telling time, they were decoding what they saw as the universe's heartbeat. Fast forward to modern science, and we're discovering they might have been closer to the truth than we imagined. Consider the way planets orbit stars. Those elliptical paths aren't random. They follow precise mathematical rhythms, governed by gravity in a dance that repeats over and over. Even on a grander scale, galaxies spin in predictable patterns, their arms sweeping through space like the hands of a clock. And then there's the mind-bending idea of cosmic inflation, the theory that our universe might be just one in an endless series, expanding and contracting in cycles stretching across billions of years. But here's where it gets really fascinating. If these cycles exist, they challenge something fundamental, our perception of time itself. We're used to thinking of time as linear, always moving forward. But what if it's more like a spiral, where events echo across epochs? Some physicists speculate that even black holes, those mysterious cosmic vacuum cleaners, might play a role in this grand cycle, swallowing matter only to eventually release it back into the universe in some form, resetting the cosmic clock. This isn't just about astronomy, it reshapes how we see existence. If the universe truly operates in these immense, repeating rhythms, then everything from the birth of stars to the structure of space itself might be part of a vast, self-regulating system. A system where the past isn't just history, it might be a preview of what's to come. Long before telescopes or satellites, ancient civilizations gazed at the heavens and saw something modern science is only beginning to fully grasp: a universe governed by rhythmic, repeating patterns. The Mayans didn't just track days and seasons. They built an entire cosmology around the idea that time moved in grand, interlocking wheels. Their long count calendar, spanning over 5,000 years, wasn't merely a way to mark dates. It was a map of cosmic cycles, predicting everything from planetary alignments to mythical epochs they believed would repeat. Even their architecture, like the Pyramid of Kukulkan at Chichen Itza, was designed to interact with celestial events, casting serpent-like shadows during equinoxes, as if the building itself were a cog in some celestial mechanism. The Egyptians took this concept even further. Their obsession with the star Sirius wasn't just about navigation. It was tied to the Nile's annual flooding, which coincided with Sirius rising just before dawn. To them, this wasn't coincidence. It was proof the universe operated on a schedule, with gods and nature moving in sync. The Great Pyramid's alignment with Orion's belt suggests they saw the stars as more than distant lights. They were a blueprint, a celestial clock face where the positions of constellations marked divine timekeeping. Then there's Stonehenge, that mysterious ring of stones on the English plains. For centuries, people assumed it was just a primitive calendar, but recent studies reveal its design could predict lunar eclipses and solstices centuries in advance. The builders didn't just observe the sky, they encoded its rhythms into stone, creating a monument that functioned like a prehistoric astronomical computer. What's striking isn't just their accuracy, it's their shared belief that time wasn't a straight path but a circle. The Babylonians compiled detailed records of Venus's movements, noticing its 8-year cycle long before modern astronomy confirmed it. Their myth spoke of cosmic battles repeating across ages, mirroring the planet's endless dances. These cultures, separated by oceans and millennia, all arrived at the same profound insight: the universe doesn't just move, it breathes, pulses, and returns. Today, we might dismiss these ideas as mere mythology, but consider this. When modern physicists talk about oscillating universes or cyclic cosmology, they're echoing the same intuition, that existence might be less like a story and more like a song, with verses that repeat across scales we're only beginning to measure. The real question isn't whether these ancient observers were right in every detail, but why so many of them, independently, saw the cosmos not as chaos but as clockwork. Johannes Kepler didn't just study the planets, he cracked open the cosmic code hidden in their motion. At a time when most astronomers still clung to the idea of perfect circular orbits, Kepler made a startling discovery: planets don't move in flawless circles around the sun. Instead, they trace elegant, oval-shaped paths called ellipses, speeding up as they swing closer to the sun and slowing down as they drift farther away. This wasn't just a minor tweak to existing theories, it was a revolution, revealing a universe governed by precise, mathematical rhythms. Kepler's first law shattered centuries of assumption. Imagine the shock when he proved that even something as majestic as a planet's orbit defied the ancient ideal of perfect symmetry. But it was his second law that truly hinted at celestial clockwork. A planet sweeps out equal areas in equal times, meaning its speed isn't random but perfectly synchronized with its distance from the sun. Picture a figure skater pulling their arms in to spin faster. The same physics scaled up to cosmic proportions, and then came his third law, a breathtaking equation linking a planet's orbital period to its average distance from the Sun, proving that the solar system operated like a meticulously calibrated machine. What makes these laws so extraordinary isn't just their accuracy, it's how they transformed our understanding of the heavens. Before Kepler, planetary motion seemed chaotic, unpredictable. After him, astronomers could calculate positions years in advance with pinpoint precision. His work didn't just describe how planets moved, it suggested why, as if some unseen hand had wound up the solar system like a grand timepiece, setting it in motion according to immutable rules. This was the moment astronomy shifted from mysticism to mathematics. Kepler's laws became the foundation for Newton's theory of gravity, revealing an invisible force that held the cosmos together. But more than that, they planted an idea. If planetary orbits followed such exacting patterns, what else might? Could the swirling of galaxies, the pulse of stars, even the expansion of space itself obey similar rhythms? Kepler's ellipses weren't just paths through space, they were clues, pointing to a universe far more orderly, far more intricate than anyone had dared to dream. Isaac Newton took Kepler's celestial rhythms and revealed the mechanism behind them, a universe ticking with such precision, it might as well have been crafted by a divine watchmaker. Picture a colossal clock, its gears invisible but undeniable, every celestial body moving in perfect obedience to unseen laws. That was Newton's revolutionary vision. When he formulated his law of universal gravitation, he didn't just explain why apples fall to the ground, he unlocked the force that binds moons to planets, planets to stars, and stars to galaxies. Suddenly, the cosmos wasn't a realm of chaos or celestial whims. It was a vast, interlocking system where every motion could be predicted with mathematical certainty. Newton's equations revealed something astonishing. The same force that pulled a dropped book to the floor also kept the moon in orbit around Earth. This wasn't just a scientific breakthrough, it was a philosophical earthquake. If the universe operated like clockwork, then everything from the trajectory of a cannonball to the dance of distant comets was governed by the same unyielding rules. The implications were staggering. Philosophers like Voltaire and Laplace seized on this idea, envisioning a cosmos so deterministic that, given enough knowledge, one could calculate every future event with perfect accuracy. Laplace famously imagined a hypothetical intellect later called Laplace's demon that could know the position and momentum of every particle in the universe and thus foresee its entire destiny. But Newton's clockwork universe wasn't just about prediction. It reshaped humanity's place in the cosmos. No longer were celestial events the capricious acts of gods, they were the inevitable outcomes of natural laws. This shift didn't just empower scientists, it inspired poets, artists, and thinkers to see the universe as a realm of order and harmony. Alexander Pope captured the awe of the era in his epitaph for Newton. Nature and nature's laws lay hid in night. God said, "Let Newton be." And all was light, yet for all its brilliance, Newton's vision had limits. His laws worked flawlessly for planets and cannonballs, but they couldn't explain everything. The erratic wobble of Mercury's orbit, for instance, defied Newtonian predictions. A tiny but persistent hiccup in the cosmic clockwork that would later lead Einstein to uncover the even deeper rhythms of relativity. And then there was the question of who or what wound up the clock in the first place. Newton himself believed divine intervention was occasionally needed to keep the celestial machinery running smoothly, a notion later scientists would challenge. Still, the legacy of Newton's clockwork universe endures. It taught us to look for patterns in the chaos, to trust that the cosmos operates by rules we can uncover. And in a way, it set the stage for every scientific revolution to come, from quantum mechanics to string theory, each one probing whether the universe is a perfect mechanism, a living system, or something stranger still. The question Newton left us with isn't just how the clock ticks, but whether it might yet surprise us. Albert Einstein didn't just tweak Newton's clockwork universe, he rewrote it entirely, revealing a cosmos where time itself bends and warps like fabric. Imagine throwing a heavy ball onto a stretched-out sheet. The depression it creates isn't just a dent in space, but in time too. This was the radical insight of relativity, that time and space aren't separate, rigid backdrops to the universe's motion. They're fluid, interwoven dimensions shaped by the very matter and energy they contain. Planets don't just orbit the sun because of some invisible force. They roll along curves in space-time, like marbles spiraling into a bowl. But here's where it gets even more intriguing. While Einstein's theories shattered the idea of absolute time, they also uncovered a hidden symmetry, a deeper order beneath the apparent chaos. Take gravitational waves, for example. These ripples in space-time, first detected in 2015, aren't random disturbances. They follow precise mathematical patterns, propagating outward like concentric rings from a pebble dropped in a pond. Even black holes, those cosmic anomalies where time seems to stop, obey strict rules, merging in predictable ways, their collisions ringing spacetime like a bell with tones physicists can actually calculate. Then there's the strange dance of time dilation. Clocks on GPS satellites tick slightly faster than those on Earth, not because of some malfunction, but because time itself runs slower the closer you are to a massive object. This isn't science fiction, it's measurable, predictable, and essential for your phone's navigation to work. And if time can stretch and compress like this, what does that say about the universe's underlying rhythms? Could these variations be part of some grander, cyclical pattern? Einstein's equations also hinted at something even more astonishing. The possibility of closed time-like curves, paths through spacetime that loop back on themselves. While these don't necessarily mean time travel in the classic sense, they suggest that under extreme conditions, the universe might permit events to echo or repeat in ways that defy linear intuition. Some physicists speculate that on cosmic scales, the twisting of spacetime near objects like rotating black holes could create natural time loops, where the fabric of reality folds back like a Mobius strip. What emerges from all this isn't chaos, but a new kind of order, one where the rigid gears of Newton's clock give way to something more like a symphony, with time and space as dynamic instruments playing in harmony. The universe, it seems, isn't just ticking, it's breathing, pulsing, and perhaps even recycling itself in ways we're only beginning to fathom. What if the Big Bang wasn't a one-time event, but just the latest tick of a cosmic metronome, a single beat in an endless rhythm of universes being born, dying, and reborn? This is the bold vision of cyclic cosmology, a modern scientific framework that echoes ancient beliefs in eternal return, but with equations to back it up. The Big Bounce theory, for instance, suggests our expanding universe might one day stop stretching outward, reverse course, and collapse back into an ultra-dense state, only to rebound in a new Big Bang, starting the cycle all over again. It's like watching a balloon inflate, deflate, and inflate anew, except on a scale where each breath lasts billions of years. The elegance of this idea lies in its symmetry. Ancient Hindu texts described cosmic cycles of creation and destruction lasting trillions of years, while Stoic philosophers imagined the universe burning up and reforming in identical patterns, what they called the Great Year. Today's physicists arrive at a startlingly similar conclusion through math, proposing that dark energy, the mysterious force accelerating our universe's expansion, might someday decay or reverse, pulling everything back together. Some models even suggest that the collisions of higher dimensional branes in string theory could trigger cyclical births of universes, like sheets of paper slapping together to spark new beginnings. But how would such a cycle leave traces? One clue might lie in the cosmic microwave background, the afterglow of the Big Bang. If a previous universe existed, some theorists argue its black holes could have left imprints in this radiation, like faint fingerprints on a window between epochs. Others propose that the universe's geometry could hold hints. A closed, spherical shape might favor a big crunch, while an open, saddle-shaped one could mean endless expansion. Then there's the mind-bending possibility that each cycle isn't identical, that physical constants like gravity's strength might reset slightly differently each time, creating variations in the cosmic recipe. What's remarkable isn't just the science, it's the philosophical mirror these theories hold up to ancient wisdom. The Mayan concept of world ages, the Buddhist idea of kalpas, even Nietzsche's eternal recurrence all envision time as a wheel rather than an arrow. Modern physics, armed with quantum equations and telescope data, now grapples with the same profound question. Are we living through a chapter that's been written before, or is the universe improvising as it goes? The answer might lie in the fabric of spacetime itself, where the past, present, and future could be threads in a tapestry far more intricate and cyclical than we ever imagined. Deep in the fabric of space, two invisible forces shape the universe in ways we're only beginning to understand: dark matter and dark energy. Picture an iceberg. What we see, stars, planets, galaxies, is just the tip. The rest, the hidden bulk, is dark matter, an enigmatic substance that doesn't emit light but exerts a gravitational pull strong enough to sculpt the cosmos. Without it, galaxies would fly apart like spinning tops losing their strings. Its gravitational grip binds clusters of galaxies together, creating vast cosmic webs that stretch across billions of light years. But here's the twist: dark matter isn't just holding things together, it might be setting the stage for the universe's grand cycles. Then there's dark energy, the even more mysterious counterpart. While dark matter pulls, dark energy pushes, acting as a kind of anti-gravity that accelerates the expansion of the universe. Imagine blowing up a balloon with dots on its surface. The dots' galaxies move apart faster as the balloon inflates. That's dark energy at work, stretching space-time itself. But what makes this so fascinating is the tension between these two forces. Dark matter's gravity tries to slow the expansion, while dark energy speeds it up. Their cosmic tug-of-war could determine whether the universe keeps expanding forever, collapses back on itself, or even enters a new cycle of rebirth. Some theories suggest dark energy isn't constant, that it might weaken or strengthen over time, altering the universe's expansion rate. If it decays, gravity could eventually gain the upper hand, pulling everything back in a big crunch. If it grows stronger, the universe might rip apart in a big rip. But there's a third possibility. Dark energy could oscillate, waxing and waning in a rhythm that triggers repeated cycles of expansion and contraction. This idea resonates with ancient visions of a cyclical cosmos, but now with equations to back it up, the clues might lie in the large-scale structure of the universe. Dark matter's gravitational scaffolding guides where galaxies form, creating patterns that echo across the cosmos. If these patterns repeat over unimaginable timescales, they could hint at deeper, recurring rhythms. Meanwhile, subtle variations in the cosmic microwave background, the afterglow of the Big Bang, might reveal how dark energy has behaved over billions of years, like fingerprints left on the fabric of spacetime. What's at stake isn't just the fate of the universe, it's the very nature of time and existence. If dark energy and dark matter operate in cycles, then the universe might not have a single linear story. Instead, it could be a symphony of expansion and contraction, creation and dissolution, playing out on scales so vast they defy human imagination. The irony is profound. The darkest, most invisible parts of the cosmos could hold the brightest revelations about where we've been and where we're headed. Galaxies spin through the void like vast, silent clock hands, each one moving with a precision that defies simple explanation. Take our own Milky Way. It completes a full rotation roughly every 250 million years, with stars nearer the center whirling faster than those on the outskirts. But here's the puzzle according to Newton's laws. Outer stars should lag far behind, like runners losing steam on a track. Instead, they keep pace, as if some invisible conductor is synchronizing their motion. This anomaly isn't unique to our galaxy. Across the universe, spiral galaxies rotate with a uniformity that gravity alone can't account for, hinting at forces or principles we've yet to uncover. Enter dark matter, the elusive substance thought to make up 85% of the universe's mass. Most scientists believe its gravitational influence explains why galaxies don't fly apart. Picture a spinning vinyl record. The visible stars are like glitter sprinkled on its surface, while dark matter is the unseen bulk of the record itself, providing the heft needed to keep everything in sync. Yet even this explanation leaves gaps. Some galaxies rotate so uniformly that they challenge dark matter models, their outer stars moving almost too cohesively, as if glued to an invisible framework. Then there's the even stranger phenomenon of galactic synchronization, clusters of galaxies millions of light years apart somehow aligning their spins in ways that defy chance. Studies of thousands of spiral galaxies reveal a peculiar pattern. Their rotation axes aren't randomly oriented. Instead, they appear correlated across vast distances, like countless compass needles mysteriously pointing the same way. This isn't just a fluke. The odds of it happening randomly are astronomically low. Could there be cosmic scale forces or fields, still unknown to science, nudging galaxies into these alignments? One provocative theory suggests the early universe might have imprinted these patterns during inflation, the rapid expansion moments after the Big Bang. Quantum fluctuations stretched to galactic scales could have created subtle directional biases like wrinkles in spacetime that guided how galaxies would later spin. Others propose that dark matter isn't just a passive scaffold but an active participant, flowing in rivers that choreograph galactic motion. And then there's the radical idea that gravity itself operates differently on cosmic scales, a notion that would upend Einstein's relativity. What's clear is this: the synchronized dance of galaxies isn't just a curiosity, it's a clue. Whether it points to hidden dimensions, undiscovered particles, or flaws in our understanding of gravity, these rotations remind us that the universe is far more interconnected, far more finely tuned than we ever imagined. The cosmos doesn't just move, it keeps time, and we're only beginning to hear its rhythm. At the smallest scales of reality, time might not flow the way we experience it. Instead, it could twist, loop, and even fold back on itself. Quantum mechanics, the rulebook for particles smaller than atoms, reveals a world where the usual laws of cause and effect blur into something far stranger. Take the famous double-slit experiment. When a single particle is fired at a barrier with two openings, it doesn't just pass through one or the other. It behaves as if it passes through both simultaneously, creating an interference pattern as if it were a wave. But here's where it gets truly bizarre. If you try to measure which slit the particle actually went through, the interference pattern vanishes, as if the particle chooses a path only when observed. This suggests that at the quantum level, particles exist in a haze of possibilities until the moment of measurement forces them to decide. Some physicists speculate this isn't just randomness, it could hint at a deeper, cyclic nature of time at microscopic scales, where potential outcomes reverberate like echoes in a closed loop. Entanglement adds another layer to this mystery. When two particles become entangled, changing the state of one instantly affects the other, no matter how far apart they are, even across galaxies. Einstein famously called this spooky action at a distance, but what if it's not spooky at all? What if it's evidence of a hidden symmetry, a thread connecting events outside linear time? Experiments have shown entangled particles seeming to coordinate their states faster than light could travel between them, as if time and space aren't the barriers we think they are. This has led to radical proposals like the transactional interpretation of quantum mechanics, where particles exchange signals not just forward in time but backward too, creating a kind of handshake across moments. Now imagine scaling up these quantum quirks to cosmic proportions. If particles can exist in superpositions, multiple states at once, could the universe itself be in a superposition of cycles, with each big bang a new branch in an infinite tree of possibilities? The idea of quantum cosmology suggests just that. Our universe might be one of countless iterations, each with slightly different physical constants, playing out in an endless fractal dance. Even black holes, those cosmic vacuum cleaners, might not be in points but portals, their singularities birthing new universes with recycled spacetime, like seeds scattered from a dying star. The parallels between quantum cycles and cosmic ones are striking. Just as a particle's wave function collapses into a definite state, perhaps universes collapse into specific configurations through cycles of expansion and contraction. And if entanglement links particles across space, could some deeper principle link universes across time? It's a dizzying thought, but it echoes ancient intuitions that the macrocosm and microcosm reflect one another, from the spin of electrons to the whirl of galaxies. The universe might not just have rhythms, it could be a symphony of cycles, each note resonating across scales we're only beginning to perceive. Black holes aren't just cosmic vacuum cleaners, they might be the universe's master regulators, fine-tuning the flow of energy and matter like gears in an unimaginably vast machine. Picture a supermassive black hole at the heart of a galaxy, its gravity so intense that not even light can escape. Yet, paradoxically, these objects don't just consume, they also shape and sustain. Jets of energy shooting from their poles stretch thousands of light years, heating surrounding gas and preventing it from collapsing into new stars too quickly. In this way, black holes act like cosmic thermostats, controlling the pace of galactic evolution. Without them, galaxies might burn through their star-forming fuel too fast, leaving behind barren wastelands instead of vibrant stellar nurseries. Their life cycles add another layer to this rhythm. A black hole begins when a massive star collapses, its core condensing into a singularity, a point of infinite density. From there, it grows by devouring nearby gas, dust, and even other stars. But here's the twist: black holes aren't eternal. Thanks to quantum effects near their event horizons, they slowly leak energy in the form of Hawking radiation, evaporating over trillions of years. This means every black hole has a birth, a life of growth and activity, and eventually a death, a cycle as fundamental as the life and death of stars themselves. Now imagine this process repeating across cosmic time. When a black hole evaporates, does its energy disperse into the void, or could it somehow seed the next cycle of creation? Some theories suggest that the information swallowed by black holes isn't lost forever but encoded in their radiation, like a cosmic blueprint waiting to be reused. Others propose that the singularity at a black hole's core might birth an entirely new universe with its own physical laws, a fractal branching of realities where each cycle spins off fresh beginnings. The most striking evidence for black holes as regulators comes from their relationship with galaxies. Observations show that the mass of a galaxy's central black hole is eerily proportional to the mass of its surrounding stars. This correlation suggests a feedback loop, black holes growing just enough to temper star formation, but not so much that they stifle it entirely. It's as if the universe has calibrated these monstrous entities to maintain balance, like a pendulum swinging between chaos and order. Could this be part of a grander pattern? If black holes help govern galaxy growth and galaxies themselves cluster in repeating large-scale structures, then these cosmic behemoths might be more than outliers. They could be keystones in an architecture of cycles spanning the entire cosmos. From their explosive births to their whisper-quiet deaths, black holes seem less like destroyers and more like conductors, orchestrating the universe's rhythms one gravitational note at a time. The cosmic microwave background isn't just a faint glow, it's the universe's oldest photograph, a snapshot frozen in time from when the cosmos was a mere 380,000 years old. Stretch your hand toward an old analog television set tuned to static, and about 1% of that snowy haze comes from this primordial light, echoing across 13.8 billion years of expansion. But buried within this seemingly uniform sea of microwaves are tiny ripples, fluctuations in temperature no larger than 1 part in 100,000. These aren't random noise, they're cosmic hieroglyphs encoding secrets about the universe's birth, its shape, and perhaps even its cycles. When scientists first mapped these fluctuations with satellites like Cobe and Planck, they expected chaos. Instead, they found patterns, subtle peaks and valleys in the temperature data that matched precise mathematical predictions. The most striking of these is the cosmic power spectrum, a graph that shows how much the temperature varies across different angular scales. Like a musical chord played on spacetime itself, these peaks correspond to sound waves ricocheting through the early universe's superheated plasma, frozen in place when light finally broke free from matter. The spacing of these peaks isn't arbitrary. It reveals the universe's geometry, confirming it's flat to within a razor's edge, a critical clue for cyclical models. If the cosmos had even slight curvature, it would warp these patterns like a funhouse mirror. But here's where it gets tantalizing. Some researchers argue these fluctuations might hold echoes of a universe before ours. The idea is controversial, but if the Big Bang was preceded by a previous cosmic cycle, its gravitational waves could have imprinted faint, swirling patterns called B-modes in the CMB. Think of it like finding fossilized footprints on a beach, evidence that something monumental passed this way long before the tide rolled in. Experiments like BICEP and the Simons Observatory are hunting for these signals, which would appear as a distinct curl in the polarization of the microwaves. Then there's the mystery of the CMB's cold spot, a region in the southern sky significantly cooler than the surrounding average. One explanation: it could be a bruise left by a collision with another universe in the multiverse, or a relic of a previous cycle's topology. Others suggest it's just statistical noise, but the odds of such a large anomaly occurring randomly are less than 1 in 100. Whether it's a cosmic glitch or a window into something grander, these anomalies remind us that the CMB isn't just a relic, it's a puzzle box waiting to be cracked open. What's remarkable is how these observations dovetail with ancient intuition. Hindu cosmology spoke of universes breathing in and out over epochs called kalpas, while some indigenous traditions describe time as a serpent eating its own tail. Today, we pass those same ideas through the language of quantum fluctuations and tensor modes. The CMB doesn't just connect us to the universe's infancy. It's a bridge between the oldest human questions and the newest scientific frontiers, asking, in microwaves and mathematics, whether the cosmos has done this all before. Pulsars are the universe's metronomes, cosmic lighthouses, blinking with such precision they rival the most accurate atomic clocks on Earth. Born from the explosive deaths of massive stars, these rapidly spinning neutron stars pack the mass of our Sun into a sphere no wider than a city. As they rotate, beams of radiation shoot from their magnetic poles like interstellar searchlights, sweeping across space with such predictable timing that astronomers can set their watches by them. The first pulsar discovered, nicknamed CP1931, stunned scientists in 1967 with pulses arriving every 1.337 seconds, a rhythm so exact it was initially mistaken for an artificial signal, earning it the playful name, Little Green Men 1. What makes pulsars extraordinary isn't just their regularity, it's what their stability reveals about the fabric of space-time. The fastest known pulsar, PSRJ0740, spins a staggering 716 times per second. Imagine a skyscraper-sized object rotating faster than a blender blade, yet its pulses arrive with deviations of less than 1/1,000,000th of a second over decades. This isn't just a curiosity, it's a cosmic laboratory. By tracking these pulses, scientists have confirmed Einstein's theory of general relativity with unprecedented precision, observing how gravity from nearby stars subtly delays the pulse's arrival, a phenomenon called the Shapiro time delay. Pulsars also serve as galactic GPS beacons. The timing of their pulses changes slightly as they move through space, allowing astronomers to map their trajectories and even detect the faint ripples of gravitational waves warping the spacetime between us and them. The Nanograv project, for instance, uses a network of millisecond pulsars, old pulsars spun up by accreting matter from a companion star, to create a galaxy-sized gravitational wave detector. These ancient timekeepers are so sensitive they can pick up distortions in spacetime caused by supermassive black holes merging billions of light years away. But perhaps the most tantalizing possibility is that pulsars might hold clues to the universe's cyclical nature. Some theories suggest their spin-down rates, the gradual slowing of their rotation, could encode information about previous cosmic cycles, like tree rings preserving Earth's climatic history. Others speculate that certain pulsar glitches, sudden speed-ups in rotation, might hint at interactions with exotic phenomena like quantum vortices in their superfluid cores. Whether as natural clocks, relativity probes, or potential time capsules, pulsars remind us that the cosmos doesn't just keep time. It is time woven into the very spin of these stellar remnants. Out in the vast expanse of the cosmos, far beyond our solar system, worlds dance to rhythms that would make even the most precise Swiss watch seem clumsy. Astronomers studying exoplanets, planets orbiting other stars, have uncovered something extraordinary. Many of these distant worlds don't just orbit randomly. Instead, they move in perfect synchrony, their paths locked into mathematical harmonies known as orbital resonances. Picture two planets circling their star like runners on a track, where for every 3 laps one completes, the other finishes too, a celestial waltz that repeats without fail, century after century. The TRAPPIST-1 system, 39 light-years away, offers one of the most stunning examples. Here, 7 Earth-sized planets orbit so tightly that a year on some lasts just a few Earth days. But what's truly mesmerizing is how their orbits intertwine. The second and third planets, for instance, resonate in a 3:2 ratio, meaning when the inner planet completes 3 orbits, the outer one finishes exactly too. This isn't a coincidence, it's a delicate gravitational balancing act where the planets tug on each other just enough to stay in sync, like pendulums subtly influencing one another's swing. These resonances aren't just pretty patterns, they're cosmic fingerprints, revealing the hidden forces shaping planetary systems. In our own solar system, Neptune and Pluto share a similar resonance, with Pluto completing 2 orbits for every 3 of Neptune's, a dynamic that prevents them from ever colliding despite their paths crossing. But exoplanets take this harmony to new extremes. Some systems, like Kepler 223, host planets locked in chains of resonances, where each world's orbit syncs with its neighbors in a domino effect of precision. How do these resonances form? Imagine a newborn planetary system, its planets still jostling for position. Over millions of years, gravitational nudges push some into stable, rhythmic arrangements while others are ejected entirely. It's survival of the most harmonious and natural selection where only the planets that find the right cadence endure. The result is a universe filled with systems that operate like clockwork, their mechanics so exact that astronomers can predict their movements centuries in advance. Yet these resonances also hint at something deeper, a universe where chaos gives way to order, where the randomness of cosmic collisions somehow produces rhythms as reliable as a metronome. Whether it's the resonant moons of Saturn or the synchronized exoplanets light years away, these patterns suggest an underlying symmetry, a cosmic preference for harmony over disorder. And if that's true, then the universe might not just be a place where things happen, but where they repeat in beats and cycles we're only beginning to trace. The Fibonacci sequence isn't just a math class curiosity, it's woven into the very fabric of the cosmos, from the swirl of galaxies to the dance of planets. Take a sunflower's spirals or a nautilus shell's chambers, and you'll see this famous pattern. Each number is the sum of the 2 before it, creating a rhythm that nature seems to adore. But step back into the vastness of space, and the pattern doesn't fade, it scales up, revealing a universe that might be humming with mathematical harmony. Spiral galaxies like our Milky Way are the most stunning examples. Their arms don't spiral randomly, they follow logarithmic curves that closely match the Fibonacci sequence's growth. The Whirlpool galaxy, 50 million light-years away, unfurls its arms in a near-perfect golden spiral, a shape whose expansion ratio mirrors the golden ratio, approximately 1.618. This isn't coincidence. As stars and gas orbit the galactic center, density waves compress material into these spirals, with each turn wider than the last by that mystical factor. It's as if the universe has a favorite blueprint, one that balances tight, winding, and expansive grace with mathematical precision. Even planetary orbits whisper Fibonacci's name. While not perfectly aligned, the spacing of planets in our solar system echoes ratios found in the sequence. Venus, for instance, orbits the Sun 13 times for every 8 Earth years, a 5:8 ratio, 2 consecutive Fibonacci numbers. Jupiter's moons Europa and Io exhibit a similar resonance, their orbital periods locked in a 2:1 ratio, another Fibonacci echo. These harmonies stabilize their paths, preventing chaotic collisions over billions of years. The deeper question is why. Some scientists argue it's a natural outcome of gravitational dynamics systems finding stable configurations through iterative tugs, much like a pendulum settling into rhythm. Others wonder if there's a deeper, almost philosophical resonance, that the same math governing pine cones and hurricanes might also shape star systems because it's the universe's most efficient way to grow, pack, and balance. Whether through physics or something more profound, the Fibonacci sequence hints that the cosmos isn't just vast, it's elegant, repeating its favorite patterns like a composer revisiting a cherished melody. Time crystals sound like something ripped from a science fiction novel, structures that pulse and cycle without ever winding down, defying one of physics' most sacred laws, the arrow of time. Unlike ordinary crystals where atoms arrange themselves in repeating patterns in space, time crystals exhibit patterns that repeat in time. Picture a diamond that doesn't just sit still but breathes, its atoms oscillating between states like a pendulum swinging forever without a push. The wildest part, these oscillations happen without any energy input, as if the universe handed them a perpetual motion cheat code. This bizarre behavior was first proposed in 2012 by Nobel laureate Frank Wilczek, who wondered whether matter could spontaneously break time symmetry, just as regular crystals break spatial symmetry. At first, many physicists dismissed the idea as impossible, since it seemed to flirt with perpetual motion, a long-standing taboo. But by 2017, teams at Harvard and the University of Maryland had created time crystals in the lab using chains of ytterbium atoms and diamond flaws, chilling them to near absolute zero and nudging them with lasers. The atoms didn't settle into equilibrium. Instead, they flipped between states at fixed intervals, locked in a rhythm that couldn't be explained by classical physics. What makes time crystals so tantalizing isn't just their novelty, it's how they echo the cyclical patterns we see across the cosmos. On a quantum scale, they mirror the universe's grand repetitions, planets orbiting, galaxies spinning, even the hypothetical cycles of cosmic inflation and collapse. Some researchers speculate that time crystals could be a microscopic window into how time itself might loop or fold under extreme conditions, like those near black holes or during the universe's birth. If matter can encode time's rhythms, could the universe be doing the same on a colossal scale? There's also a practical side to this mystery. Time crystals might one day revolutionize quantum computing, offering a stable, error-resistant way to store information in their unyielding cycles. But beyond their utility, they challenge our deepest assumptions. For centuries, we've seen time as a river flowing one way. Time crystals suggest it might also have eddies and whirlpools, places where it curls back on itself, if only for a fleeting quantum moment. In a universe where even matter can tick like a clock, the line between time and substance blurs, hinting at a reality far more interconnected and far stranger than we ever dreamed. The idea of a multiverse doesn't just expand our cosmic horizons, it might weave them into an even grander tapestry of repeating rhythms. Imagine not just one universe pulsing through cycles of birth and rebirth, but countless others, each with its own tempo, its own rules, yet somehow harmonizing in a symphony of existence. This is where cyclic cosmology collides with multiverse theory, and the implications are as dizzying as they are profound. Take the concept of eternal inflation, where our universe is just one bubble in a frothing sea of spacetime, endlessly spawning new universes with every quantum fluctuation. In this view, each bubble universe could follow its own cycle, expanding, cooling, and perhaps collapsing, only to rebound anew. But here's the twist: if these universes aren't entirely isolated, their cycles might influence one another. Picture two pendulums hanging side by side. Even if they start swinging at different times, their motions can synchronize through subtle vibrations. Could cosmic cycles work the same way, with universes subtly nudging each other into alignment across dimensions we can't yet perceive? Then there's string theory's vision of the multiverse, where higher dimensional brains float like sheets of paper in a cosmic wind. When these brains collide, they might trigger big bangs not once, but over and over, in rhythms dictated by their trajectories. Some models suggest these collisions could be periodic, with universes like ours arising at regular intervals, each one a fresh verse in an endless poem. And if the brains carry echoes of past collisions, traces of previous universes might linger in the cosmic microwave background, like faint scars hinting at a history we're only beginning to decode. But what if the connections run deeper? Quantum mechanics introduces the idea of entanglement, where particles remain linked across vast distances. Could entire universes be entangled, their cycles somehow mirrored or intertwined? It's a wild thought, but some theorists propose that information, perhaps even the very laws of physics, could be shared between universes, creating a network of cosmic clockworks ticking in unseen unison. If true, our universe's constants, the strength of gravity, the mass of an electron, might not be arbitrary but shaped by these hidden relationships, the most tantalizing possibility. That cyclic universes could serve as cosmic laboratories, each iteration tweaking the rules slightly. In one cycle, gravity might be stronger, stars burning brighter and faster. In another, matter could behave differently, giving rise to structures we can't even imagine. Over countless cycles, universes might learn stable configurations, evolving toward forms that endure. It's a vision that blends science with almost mythological grandeur, a multiverse not of chaos, but of endless refinement. Whether these ideas hold up to scrutiny remains to be seen. But they remind us that the quest to understand our universe's rhythms might be just the beginning. If cycles span the multiverse, then time, space, and existence itself could be far stranger and far more interconnected than we ever dared to dream. From the earliest campfires to the glowing screens of modern life, humans have always been storytellers, and our greatest stories often revolve around cycles. The sun rises and sets, seasons turn, generations come and go. These rhythms shape not just how we live, but how we think. Ancient cultures didn't just observe these patterns. They wove them into myths that explained everything from harvests to human destiny. The Egyptian sun god Ra sailed across the sky each day, only to be swallowed by the underworld at night and reborn at dawn. The Norse envisioned time as a great serpent, Ouroboros, eating its own tail, an endless loop of destruction and renewal. These weren't just colorful tales, they were attempts to make sense of a world where everything, from the stars to the tides, seemed to move in circles. Psychologists suggest this attraction to cycles runs deep in our brains. Humans crave predictability, it's how we survive. When early hunter-gatherers noticed animal migrations or fruit-bearing trees followed reliable patterns, they could plan ahead. That same neural wiring makes cyclical time feel comforting even today. Linear time, with its uncertain future and irreversible losses, can feel like walking a tightrope without a net. But cyclical time offers a promise. What's lost will return, what's broken will be remade. This might explain why cultures facing upheaval, from the collapsing Roman Empire to indigenous tribes displaced by colonization, often turn to cyclic myths as anchors in chaos. Modern science hasn't erased this longing, it's given it new language. When astrophysicists talk about oscillating universes or quantum loops, they're tapping into the same deep-seated intuition that captivated the Mayans charting their long count calendar. Even our entertainment reflects it, from the time loop narratives of Groundhog Day to the apocalyptic rebirths of the Matrix. These stories resonate because they mirror a truth we sense but can't always prove, that existence might be less like a straight line and more like a spiral, where endings fold into beginnings. The irony is profound. Today's telescopes peer further into space than ancient shamans ever dreamed, yet what they reveal, galaxies spinning, stars being born from stellar ashes, often feels eerily familiar. Whether through myth or math, humans keep returning to the same revelation. If the universe has a heartbeat, perhaps we're all just learning to dance to its rhythm. Earth's climate has never been static. It pulses between ice ages and warm periods with a rhythm that seems almost deliberate. Over the past 2.6 million years, our planet has swung in and out of glacial periods roughly every 100,000 years, like a pendulum driven by invisible hands. But what if those hands aren't just terrestrial? Scientists are uncovering clues that Earth's climate dances to a tune played by the cosmos itself, with everything from the sun's tantrums to our galaxy's motion shaping the tempo. Take the Milankovitch cycles, the slow wobbles and tilts in Earth's orbit that nudge us toward ice ages. While these shifts, changes in axial tilt, orbital shape, and planetary wobble are homegrown, they're part of a larger gravitational symphony conducted by the planets. Jupiter's hefty pull, for instance, stretches Earth's orbit into a more elliptical shape every 400,000 years, altering how much sunlight we receive. Meanwhile, the sun's own activity ebbs and flows in 11-year cycles, with periods of intense solar storms or eerie quiet that can ripple through Earth's atmosphere, altering cloud formation and even rainfall patterns. But the cosmic connections might run deeper still. As our solar system orbits the Milky Way center, completing one lap every 225 million years, it doesn't move smoothly. It bobs up and down through the galactic plane like a carousel horse. Some researchers speculate these undulations could expose Earth to higher doses of cosmic rays during certain phases, potentially triggering cloud cover changes that cool the planet. There's even evidence that ice ages align roughly with these galactic crossings, as if the universe itself is flipping a climatic switch. Then there's the wild card of interstellar visitors. When our solar system passes through dense molecular clouds, the same nurseries where stars are born, it's bathed in a fog of dust and gas. This interstellar material might subtly dim the sun's light reaching Earth, or seed our atmosphere with particles that alter weather patterns. One provocative study suggests the youngest glacial period, 12,000 years ago, coincided with a plunge through one such cloud, as if the galaxy had breathed a frosty sigh across our world. The beauty of these cosmic climate links isn't just in their grandeur, it's in their reminder that Earth isn't an isolated bubble. We're embedded in a web of gravitational nudges, radiation tides, and interstellar winds, all ticking in rhythms that might stretch from our atmosphere to the edges of the galaxy. If that's true, then decoding Earth's past and perhaps predicting its future requires looking beyond our skies to the celestial clockwork that's been quietly shaping our home all along. Astrology and astronomy might both gaze at the stars, but their paths diverge like two rivers flowing from the same mountain, one into myth, the other into measurement. Ancient astrologers mapped the heavens not as a physical realm but as a mirror, reflecting the ebb and flow of human destiny. They saw the zodiac as a celestial clock, its 12 signs marking not just the sun's annual journey but the rhythms of fate itself. When the Babylonians divided the sky into 12 equal slices around 1800 BC, they weren't plotting orbits, they were crafting a symbolic language, linking planetary movements to harvests, wars, and kings' fortunes. The Mayans took it further, their sacred calendars tying celestial cycles to prophecies so precise they're still debated today. These systems thrived on repetition, the return of Venus as an omen, the retrograde of Mars as a portent, each cycle layered with meaning beyond mere motion. Fast forward to modern astronomy, and the sky tells a different story. Galileo's telescope didn't just magnify the stars, it shattered the astrological sky into billions of suns, each governed by laws as unyielding as they are indifferent to human affairs. Take planetary motion, where astrology interprets Mercury's retrograde as a time of miscommunication. Astronomy reveals it as a simple line of sight illusion, Earth overtaking Mercury in its orbit like a faster car on a cosmic highway. Even the zodiac's tidy 12-part division crumbles under scrutiny. Precession has shifted the sun's apparent path so that astrological signs no longer align with their namesake constellations, a discrepancy known since Ptolemy but ignored in horoscopes. Yet here's the twist: while their methods clash, both fields share a primal fascination with cosmic cycles. Astronomers may debunk astrology's causality, but they've uncovered their own breathtaking repetitions, like the way solar activity peaks every 11 years or how galaxies spin in predictable spirals. The difference lies in the lens. Astrology seeks meaning in the stars, weaving narratives where Jupiter's position might influence luck. Astronomy seeks mechanisms, using those same planetary positions to test gravity's grip or calculate orbital resonances. One system thrives on metaphor, the other on math. This tension isn't just academic, it's cultural. Millions still check horoscopes, not because they misunderstand science, but because the human mind craves patterns, especially ones that feel personal. Meanwhile, telescopes like Hubble and JWST unveil cycles far grander than any zodiac. Galaxies colliding and reforming, stars recycling their ashes into new generations. Perhaps the real divide isn't between myth and science, but between two ways of marveling at a universe that, whether by chance or design, never stops repeating itself. The Grand Tack hypothesis paints a picture of our solar system's youth that's anything but orderly, a time when planets weren't fixed in their orbits but roamed like celestial nomads, reshaping everything in their path. At the center of this cosmic drama was Jupiter, not as the stately giant we know today, but as a gravitational bulldozer plowing through the inner solar system before retreating back to its current position. This wild migration, known as the Grand Tack, didn't just shuffle planetary furniture. It might have set the stage for rhythmic alignments that echo across billions of years. Imagine the early solar system as a construction zone, with planets still settling into their orbits. Jupiter, freshly formed, began spiraling inward toward the Sun, its immense gravity clearing a swath through the primordial disk of gas and dust. But just as it neared where Mars orbits today, something remarkable happened. Saturn, growing in size and gravitational pull, began tugging Jupiter back outward, like a cosmic leash yanking the runaway planet into reverse. This gravitational dance didn't just save the inner solar system from being devoured, it sculpted it. As Jupiter swung back, its gravity shepherded leftover debris into tighter orbits, seeding the region that would become Earth and the other rocky planets. The echoes of this migration might still be visible today. Some astronomers suggest Jupiter's inward and outward journey could have locked certain asteroids and planets into resonant orbits, harmonious alignments where their paths sync up like gears in a clock. The asteroid belt's peculiar gaps, known as Kirkwood gaps, are one possible fingerprint of this process. These are regions where asteroids avoid orbiting, precisely because Jupiter's gravity nudges them away in predictable cycles. It's as if the Grand Tack didn't just rearrange the solar system, it wound up a celestial metronome, setting beats that still influence planetary motion. But the implications stretch even further. If Jupiter's migration triggered recurring alignments, could similar events shape other star systems? Exoplanet hunters have found hot Jupiters, gas giants parked shockingly close to their stars, hinting that planetary migration isn't rare. Some of these systems show signs of resonant chains, where planets orbit in precise ratios, much like the hypothetical echoes of our own solar system's turbulent youth. The Grand Tack might not be an anomaly, it could be part of a universal rhythm, where young planets waltz through their stellar neighborhoods before settling into long-term patterns. What's mesmerizing about this idea isn't just the mechanics, it's the poetry. a planet's ancient journey, written in the gravitational language of orbits and resonances, might still be ticking beneath the surface of our cosmic neighborhood. The next time you look up at Jupiter, remember, its serene glow belies a tempestuous past, one that could hold the key to understanding not just our solar system's history, but the hidden cadence of the cosmos itself. Chaos theory might seem like the ultimate rebuttal to a clockwork universe after all. It's the science of unpredictability, where tiny variations snowball into wildly different outcomes. Think of a butterfly flapping its wings in Brazil, setting off a tornado in Texas. At first glance, this appears to shatter any notion of cosmic order. But here's the paradox: chaos doesn't always lead to disorder. Instead, it can sculpt intricate, repeating patterns from apparent randomness, like a sculptor revealing hidden shapes in marble. The universe might not be a perfect Swiss watch, but it's far from a chaotic free-for-all. It's more like a jazz improvisation, where spontaneity and structure dance together in unexpected harmony. Take our solar system as an example. For centuries, astronomers assumed planetary orbits were as stable as clock gears, ticking along in perfect predictability. Then chaos theory revealed the truth. Over millions of years, gravitational tugs between planets introduced tiny uncertainties that compound into orbital shifts. Mercury, the solar system's smallest planet, is especially vulnerable. Its path could eventually become so erratic that it might collide with Venus or even veer into the Sun. Yet despite this inherent instability, the solar system has persisted for billions of years without descending into mayhem. Why? Because chaos isn't pure randomness. It operates within boundaries, like a pendulum swinging wildly but never leaving its frame. The planets may wobble, but their chaos is deterministic, governed by rules that keep their motions from spiraling into true disorder. This delicate balance shows up everywhere, from the swirl of galaxies to the pulse of stars. Consider turbulent fluids, whether in a rushing river or the churning atmosphere of Jupiter. At first glance, their motion seems utterly chaotic, but look closer and you'll spot vortices that form, dissolve, and reform in recognizable patterns. These aren't random, they're strange attractors, a hallmark of chaotic systems where motion never repeats exactly but stays within an invisible scaffold. It's as if the universe has a preference for organized chaos, where complexity arises from simple rules iterated over and over. Even the cosmos's largest structures hint at this hidden order. The distribution of galaxies across the universe isn't random, it's fractal, with clusters and voids repeating at different scales like a cosmic fingerprint. This self-similarity emerges from the interplay of gravity and initial quantum fluctuations, a dance of chaos and structure that began with the Big Bang. In a way, the universe is like a kaleidoscope. Shake it, and infinite variations emerge, but the underlying symmetry remains. So where does this leave the idea of a clockwork cosmos? Chaos theory doesn't dismantle the concept, it deepens it. The universe isn't a rigid machine ticking in lockstep, but a dynamic system where order and unpredictability intertwine. Patterns recur not because they're preordained, but because the laws of physics nudge chaos toward stability over time. It's a reminder that even in apparent randomness, there's a rhythm, one we're still learning to hear. What if the universe's cycles aren't just natural phenomena, but lines of code in an unfathomable cosmic program? Simulation theory, the idea that our reality might be an artificially constructed simulation, takes on a haunting new dimension when paired with the rhythmic patterns we see across the cosmos. Think of the way planets orbit in predictable ellipses, galaxies spin with mathematical precision, or even quantum particles flicker between states like binary digits. Could these repetitions be glimmers of underlying programming logic, a universe running on loops and subroutines? the concept isn't as far-fetched as it sounds. Philosopher Nick Bostrom's famous simulation argument posits that if advanced civilizations could create ancestor simulations, hyper-realistic virtual worlds populated by conscious beings, the statistical likelihood we're in the base reality shrinks to near zero. Now layer cyclic cosmology onto that idea. If the universe resets or repeats, might each iteration be a fresh simulation run, tweaking variables to observe different outcomes? From a scientific standpoint, the idea gains traction in unexpected places. Take the fine-tuning of physical constants, the eerie precision of numbers like the gravitational constant or the mass of an electron, all calibrated just right for life to exist. In a simulation, these could be adjustable parameters set by the programmers to test different scenarios. Even quantum mechanics, with its probabilistic quirks, fits oddly well with the concept of optimized computation. The universe doesn't render every possible state simultaneously. It calculates outcomes only when observed, like a video game loading graphics only when a player looks. And those cosmic cycles, they could be memory-saving mechanisms, recycling energy and matter to keep the simulation efficient, but critics push back hard. Physicist Sabine Hossenfelder argues that invoking simulation as an explanation is a modern-day God of the gaps, a placeholder for mysteries we haven't yet solved. Why assume a simulator when natural laws suffice? Others point out that if the universe were a simulation, we'd expect shortcuts or glitches, like computational limits on small scales. Yet quantum physics operates flawlessly down to Planck lengths with no signs of pixelation. And then there's the philosophical quagmire. If we're in a simulation, who's running it? Another simulated civilization that leads to an infinite regress, a cosmic matryoshka doll of simulations within simulations. Perhaps the most compelling middle ground lies in the language of mathematics. Whether the universe is real or simulated, its patterns are undeniably algorithmic, governed by equations that generate complexity from simplicity. The Fibonacci sequence in galaxies, the harmonic resonances of planetary orbits, even the fractal branching of lightning, all emerge from mathematical rules. In that sense, the universe does run on code, whether it's the abstract laws of physics or literal programming. The difference might be semantic. What we call nature, a simulator might call source code. This isn't just speculative fun, it reshapes how we view existence. If cycles hint at a simulated reality, then free will becomes a haunting question. Are our choices our own or predetermined loops in the program? Is the search for cosmic meaning just debugging someone else's creation? Or conversely, does it elevate our place in the cosmos? After all, even if we're just code, we're code complex enough to question its own programming, a meta layer the simulators might not have anticipated. The beauty of this paradox is that it bridges ancient and modern, from Hindu texts describing reality as Maya illusion to Elon Musk joking about our odds being 1 in billions of living in base reality. Whether simulation or not, the universe's rhythms remind us that reality, whatever its nature, is far stranger and more structured than we ever imagined. The universe seems almost suspiciously well-suited for life. Alter the strength of gravity by a fraction, tweak the mass of an electron, and stars, planets, and biology as we know it would cease to exist. This eerie precision is known as the Anthropic principle, the idea that the universe's fundamental constants appear fine-tuned because, well, we're here to observe them. But what if this fine-tuning isn't a one-time cosmic fluke? What if it's the result of countless cycles, a universe iterating until the conditions for life finally click into place? Consider the numbers that make our existence possible. The cosmological constant, which drives the universe's expansion, is calibrated to 1 part in 10 to the power of 120, a value so precise that physicist Leonard Susskind compared it to hitting a bullseye on a dartboard the size of the observable universe. If it were slightly stronger, galaxies would have ripped apart before life could form, slightly weaker, and everything would have collapsed back into a singularity. Similarly, the strong nuclear force binds atomic nuclei, but if it varied by just 2%, stars couldn't produce carbon, the backbone of life. These aren't arbitrary settings, they're the Goldilocks conditions that let us exist. Now imagine a cyclical universe where each iteration tweaks these constants slightly. Most cycles might produce sterile, empty cosmos expanding too fast for stars or collapsing too quickly for chemistry. But given enough cycles, statistics suggest at least one version would stumble upon the right combination, like a gambler hitting the jackpot after infinite rolls of the dice. In this view, our universe isn't special, it's inevitable, the winning ticket in a cosmic lottery that's been running for eternity. String theory adds a provocative twist. Its landscape of possible universes suggests physical constants could vary across different regions of reality, like bubbles in an infinite foam. If each cycle of a bouncing universe resets these parameters randomly, life would only arise in the rare bubbles where the numbers align. The rest silent, barren, and unobserved. This could explain why we find ourselves in such a hospitable cosmos, because we couldn't exist in the others. But critics push back. Some argue the anthropic principle is a tautology. Of course, we observe a universe compatible with life, because we're here to observe it. Others propose alternative explanations, like undiscovered laws that lock constants into their life-friendly values. Yet the cyclical model offers something unique, a mechanism for fine-tuning without invoking a designer or multiverse. Each cycle becomes an experiment, with the universe subtly refining its parameters until life emerges. The implications are staggering. If cycles continue indefinitely, life might not be a one-time accident, but an inevitable phase in the universe's rhythm. And if the constants shift slightly with each iteration, future cycles could birth entirely new forms of existence, alien biochemistries, unfamiliar physics, realities beyond our imagination. We might be living in just one stanza of an endless cosmic poem where the verses repeat, but never quite the same way twice. The anthropic principle, then, isn't just a curiosity. It could be the key to understanding why the universe feels so perfectly timed and whether that perfection is built to last. Predicting the future of the cosmos might sound like the realm of oracles and star charts, but the rhythms of celestial clockworks could turn science fiction into scientific forecasting. Imagine a future where astronomers don't just track asteroids, they predict galaxy-scale events with the same confidence we forecast tomorrow's weather. The key lies in recognizing that the universe isn't a chaotic free-for-all. It's a tapestry of interlocking cycles, each offering clues to what comes next. Take asteroid orbits, for example. By mapping their resonant patterns, how they sync with Jupiter's gravitational tugs, we've already identified potential Earth-crossing threats centuries in advance. But what if we applied this same logic to grander scales? Galactic collisions might seem like random catastrophes, but they too follow cosmic schedules. Our Milky Way is on a collision course with Andromeda, due to merge in about 4 billion years. That prediction isn't guesswork, it's based on precise measurements of their mutual gravitational pull, a dance choreographed by the same Newtonian laws that govern pendulum swings. As telescopes grow more advanced, we could pinpoint similar fates for other galaxies, tracing their paths through the gravitational wrinkles of dark matter like ships navigating tidal currents. Even the universe's expansion, currently accelerating due to dark energy, might have cycles we've yet to decode. Some models suggest dark energy's strength could oscillate, meaning today's runaway expansion might someday reverse, triggering a universal spring after the long winter of dispersion. The real frontier, though, lies in black hole symphonics. Just as seismologists predict earthquakes by monitoring tectonic stresses, astronomers might one day forecast black hole mergers by analyzing their orbital harmonics. The LISA mission, a planned space-based gravitational wave detector, aims to map these ripples in space-time with such precision that we could anticipate collisions decades before they happen. Picture receiving an alert that two supermassive black holes, 3 billion light-years away, will spiral together in the year 2124, not because we're psychic, but because their orbital decay follows equations as reliable as a metronome's beat. Then there's the ultimate forecast, predicting the universe's next reboot. If cyclic cosmology is correct, our cosmos might collapse and rebound in a new Big Bang. While timescales here stretch beyond human comprehension, certain clues, like subtle anomalies in the cosmic microwave background or shifts in dark energy's behavior, could serve as early warning signs. It's akin to reading tree rings to reconstruct past climates, except here, the rings are imprinted in the fabric of space-time itself. Of course, these predictions hinge on uncovering deeper layers of cosmic order. Just as Kepler's laws transformed planets from celestial wanderers into predictable clock hands, future breakthroughs could reveal new symmetries hiding in plain sight. Maybe quasars flicker in coded sequences, or dark matter arranges itself in fractal patterns that hint at coming shifts. The universe's clock might be infinitely more complex than we imagine, but every tick, every tock, is a piece of a puzzle we're only beginning to assemble. And if history's any guide, the more we listen to its rhythms, the more astonishing the forecast will be. If the universe truly operates like a vast, unerring clockwork, every event predetermined by the gears of physics, where does that leave human choice? The ethical weight of this question presses down through centuries of philosophy, theology, and science. On one hand, a deterministic cosmos suggests our decisions are mere illusions, echoes of causes set in motion billions of years ago. Every thought, every act would trace back to the Big Bang like dominoes in an infinite cascade. Ancient Stoics grappled with this notion, framing fate as an unbreakable chain, yet urging people to embrace their role in the cosmic order willingly. Their solution, freedom, isn't in controlling events, but in aligning one's will with nature's rhythms, a perspective that resurfaces in modern discussions about living harmoniously within universal laws. Yet the counterargument pulses just as strongly. If the universe's cycles are predictable, doesn't that grant us a unique power, the ability to anticipate and adapt? Farmers have done this for millennia, planting and harvesting in sync with seasons they know will recur. Today, climate scientists extend this logic, using planetary cycles to model future changes and advocate for policies that align with Earth's natural cadences. In this light, determinism isn't a cage, it's a map. Knowing the tides doesn't diminish the sailor's skill, it sharpens it. The moral imperative shifts from resisting the universe's flow to learning its currents and navigating them with intention. The tension sharpens when we consider punishment and justice. If a murderer's actions were preordained by cosmic equations, can we truly blame them? Legal systems assume free will, holding individuals accountable for choices. But in a clockwork reality, guilt and innocence blur into mechanistic outcomes. Some philosophers, like Spinoza, reconciled this by redefining freedom as understanding necessity. The more we comprehend the forces shaping us, the more authentically we can act within them. Others, like existentialists, reject determinism outright, insisting that even in a patterned universe, humans carve meaning through sheer acts of will. Perhaps the most profound implication lies in how we value life itself. Cyclical time, with its endless rebirths, might render individual lives fleeting, yet paradoxically sacred. If the universe repeats, every kindness and cruelty echoes infinitely. This isn't just metaphysics, it's a mirror. Whether we see ourselves as cogs in a machine or composers of destiny shapes how we treat each other. The clockwork cosmos doesn't dictate morality. It invites us to ask, in its relentless ticking, what kind of rhythm we choose to amplify. Artificial intelligence is revolutionizing how we decode the universe's rhythms, not by replacing human curiosity, but by amplifying it to scales we could never achieve alone. Take NASA's Kepler Space Telescope, which collected data on over 150,000 stars for nearly a decade. Sifting through that mountain of information for the subtle dips in brightness signaling distant planets would take lifetimes without machine learning. But AI algorithms trained on planetary transits can spot these patterns in hours, uncovering cycles hidden in the noise. One neural network even discovered an 8-planet system by spotting a transit signal humans had missed, a cosmic drummer keeping time in a star system 3,500 light-years away. Quantum computing takes this further, probing cosmic cycles at speeds that defy classical physics. Google's Sycamore processor demonstrated this by solving a problem in 200 seconds that would take supercomputers millennia. For astrophysicists, such power could simulate galaxy formation over billions of years in days, revealing how gravitational dances between stars and dark matter create the large-scale rhythms we observe. D-Wave's quantum annealers are already modeling how black holes might emit Hawking radiation, a process theorized to span epochs, now compressed into lab timescales. These tools don't just calculate faster, they illuminate connections between cosmic cycles that were previously invisible, like uncovering harmonies in a symphony too complex for human ears to disentangle. But the real game changer lies in combining these technologies. The Vera Rubin Observatory's legacy survey of space and time will generate 15 terabytes of data nightly, more than the entire Hubble archive every week. To pass this flood, scientists are building AI that learns from quantum simulations, creating feedback loops where each informs the other. Imagine an algorithm trained on quantum models of oscillating universes, then set loose to hunt for matching patterns in telescope data. Early tests have spotted anomalies in the cosmic microwave background that could be echoes of pre-Big Bang cycles, whispers from universes past, captured by machines that think in dimensions beyond our own. Yet for all their power, these tools are just extensions of an ancient human impulse to find order in the stars. The same drive that led Babylonians to track Venus now fuels AI parsing quasar flickers for signs of hyperdimensional resonance. The difference is scale. Where once we charted cycles with stone circles and parchment, we now deploy neural networks that rediscover Kepler's laws from raw data alone, then push beyond them. The universe's clockwork may be vast, but with every algorithmic breakthrough, we're learning to listen to its ticking, not just in the present, but across the echoes of eternity. Friedrich Nietzsche's concept of eternal recurrence isn't just a thought experiment, it's a gauntlet thrown at the feet of existence itself. Picture this: every joy, every heartbreak, every mundane moment of your life destined to repeat infinitely, with no variation, no escape. This life as you now live it and have lived it, you will have to live once more and innumerable times more. He wrote in The Gay Science. For Nietzsche, this wasn't merely a poetic metaphor, it was a litmus test for authenticity. If the idea of reliving your life endlessly fills you with dread, he argued, then you're not living it right. But strip away the philosophical provocation, and you're left with a startling question. Was Nietzsche, in his own way, anticipating the cyclical cosmologies modern physicists now explore? Fast forward to today, and the parallels between Nietzsche's eternal recurrence and theories like the Big Bounce or conformal cyclic cosmology are impossible to ignore. Both envision time as a loop rather than a line where endings fold into beginnings, but where Nietzsche's cycles were metaphysical, a challenge to human meaning-making, scientific models ground them in mathematics. Roger Penrose's conformal cyclic cosmology, for instance, proposes that the universe's distant future, once all matter has evaporated into radiation, becomes mathematically indistinguishable from the ultra-smooth, low-entropy state of the Big Bang. In this view, the universe doesn't just repeat, it resets, with each aeon inheriting subtle traces of its predecessor in the form of gravitational waves or quantum imprints. The difference: Nietzsche's cycles are identical, while Penrose's allow for variation, like a record skipping slightly with each revolution. This intersection of philosophy and physics raises profound questions about agency and inevitability. Nietzsche's eternal recurrence suggests a universe where every detail is fixed, a cosmic déjà vu without deviation. Modern cosmology, by contrast, entertains the possibility that each cycle could tweak the rules, constants of nature shifting slightly, galaxies forming differently. Does that make the scientific version more hopeful or just unpredictably repetitive? The tension here mirrors an ancient debate. The Stoics saw cycles as fate to be embraced, while Buddhists viewed them as karma to be transcended. Science, in its quest for empirical truth, reframes the question: are these cycles observable, or are they, like Nietzsche's vision, ultimately a mirror held up to our hunger for meaning? Perhaps the most striking convergence lies in how both fields grapple with time's nature. Nietzsche's eternal recurrence collapses past and future into an eternal present, echoing physicist Julian Barber's controversial timeless universe hypothesis, where time is an illusion and all moments exist simultaneously. Meanwhile, the thermodynamic arrow of time, the irreversible flow from order to disorder, seems at odds with cyclical models until you consider that each universe's end might reset entropy, like a wound-up watch spring recoiling. The irony is delicious. A 19th century philosopher and 21st century physicists, separated by method and language, circling the same enigma. What emerges isn't just a dialogue between disciplines, but a challenge to our linear instincts. Whether through Nietzsche's existential lens or Penrose's equations, cyclical time forces us to confront the uncomfortable idea that innovation and novelty might be local phenomena in a grander, repetitive scheme. The stars above us may not just be distant suns, they could be echoes of a pattern older than thought itself, a rhythm that philosophers felt in their bones long before telescopes could trace its beat. In the end, the quest to understand cyclical time isn't just about physics or philosophy. It's about deciphering whether the universe is a story with an ending or a song on repeat, and what that means for the fleeting verses we call our lives. Long before telescopes or particle accelerators, humanity's storytellers were already mapping the cosmos not in equations, but in myths that saw time as a wheel, not an arrow. The Hindu concept of yugas divides existence into 4 repeating ages, each descending from golden purity to iron-clad decay before resetting in a grand cycle spanning millions of years. The current epoch, the Kali Yuga, is said to be an age of strife, yet it's also just one season in an endless cosmic harvest, destined to give way to renewal. Meanwhile, halfway across the world, Norse myths envisioned Ragnarok not as an end, but as a fiery recalibration. Gods and monsters perish in battle, only for the world to emerge fresh from the waters, with two human survivors whispering secrets of the old cycle to the new. These aren't just tales, they're ancient models of the universe, coded in symbolism but striking eerily close to modern cosmology's cycles of birth, collapse, and rebirth. The Maya took this further, their long count calendar tracking vast cycles of creation and destruction like a celestial odometer. Each sun era ended in catastrophe, floods, jaguars, hurricanes, only for the next to dawn with subtle shifts in cosmic order. Archaeologists discovered their calculations aligned with real astronomical events, like the precession of equinoxes, suggesting these weren't just myths but observations of celestial mechanics translated into narrative. Similarly, indigenous Australian traditions describe the dream time as both a primordial past and an ever-present cycle where ancestral beings shape the land in rhythms mirrored by the stars' movements. When modern physicists speak of the universe's conformal cyclic cosmology, where each eon's end becomes the next's beginning, they're walking a path first carved by storytellers around campfires millennia ago. Even Abrahamic traditions, often seen as linear in their eschatology, harbor cyclical undercurrents. Jewish mysticism's concept of Shemitah cycles 7-year periods of release culminating in a Jubilee year parallels ideas of cosmic rebalancing. Early Christian thinkers like Origen speculated about apokatastasis, a universal restoration where all souls return to divine harmony, echoing the Stoic belief in periodic conflagrations and rebirths. These parallels aren't coincidental, they are evidence of a shared human intuition that time's arrow might curve back on itself, whether through divine will or gravitational collapse. The most striking resonance lies in the details. Hindu texts describe cosmic dissolution as pralaya, where the universe dissolves into a latent state before re-emerging, a concept hauntingly similar to the Big Crunch hypothesis. Aztec mythology's 5 suns, each destroyed by elemental forces, mirror the multi-collision brains of string theory. Even the Hopi prophecy of 9 worlds, each destroyed when humanity loses harmony with nature, finds an unsettling parallel in climate science's warnings about planetary tipping points. What ancient cultures framed as moral allegories, modern science quantifies with redshift measurements and entropy calculations, but the underlying rhythm remains. Perhaps these recurring motifs reveal less about the universe's structure and more about the human mind's need to find order in chaos. Yet the uncanny alignments between myth and math suggest something deeper, that long before laboratories, humanity's first astronomers, whether charting Venus on Babylonian tablets or aligning Stonehenge to solstices, were piecing together a puzzle we're still solving. The night sky hasn't changed, only our language for its secrets has. Whether through the Epic of Gilgamesh or the equations of Penrose, we're still whispering the same question. Does the universe remember its own beginnings, and will it dare to repeat them? The year 2012 sparked a global frenzy, with doomsday prophets claiming the Mayan calendar predicted the end of the world. Headlines screamed about cosmic alignments hurling Earth into chaos, while survivalists stockpiled canned goods. But when December 21st arrived, the planet didn't implode, it just kept spinning. This wasn't the first time cosmic cycles got hijacked by apocalyptic myths, and it won't be the last. The truth, real celestial rhythms bear little resemblance to Hollywood catastrophes or conspiracy theories. They're not arbitrary expiration dates stamped on the cosmos, but intricate, measurable patterns that reveal how the universe breathes, evolves, and regenerates. Take the Mayan long count calendar, often misrepresented as a doomsday clock. In reality, it marked the completion of a 5,125-year cycle, a reset akin to flipping an odometer, not a countdown to oblivion. Modern scholars like anthropologist John Major Jenkins point out that Mayan inscriptions describe this transition as a time of renewal, not annihilation. Their astronomers tracked Venus's cycles with jaw-dropping precision, noting how its 8-year dance with Earth created a pentagram-like pattern in the sky. These weren't omens of doom, they were celestial mathematics, a way to harmonize human rituals with cosmic intervals. The irony, while alarmists fixated on an imaginary apocalypse, they overlooked the real wonder. The Mayans' sophisticated grasp of orbital mechanics achieved centuries before telescopes. Then there's the persistent myth of planetary alignments triggering disasters. Every few years, viral claims warn that planets lining up will unleash earthquakes or solar flares. But gravity doesn't work that way. Even if every planet in the solar system aligned perfectly, an event rarer than a blue moon, their combined gravitational pull on Earth would be weaker than the moon's by a factor of thousands. NASA routinely debunks these scares, noting that planetary alignments are visually striking yet scientifically mundane. The real magic lies in how these alignments demonstrate orbital resonances, like Jupiter and Saturn's 20-year meetups, which astronomers use to calibrate models of solar system dynamics. Another common mix-up conflates cosmic cycles with astrology's celestial influences. While astrology interprets planetary positions as forces shaping human fate, astronomy observes how those positions obey gravitational laws with no mystical causality. Mercury retrograde, for instance, doesn't cause technological glitches or miscommunication. It's a perspective illusion, like two cars on a highway where the faster one appears to move backward when it passes the slower. Yet this astronomical phenomenon gets blamed for everything from crashed computers to awkward family dinners, the difference between myth and science. One sees the cosmos as a fortune teller's crystal ball, the other as a clockwork masterpiece where every tick is governed by equations, not whims. Perhaps the most damaging misconception is the idea that cosmic cycles imply inevitable destruction. Yes, the universe has rhythms, ice ages, solar cycles, even galactic orbits, but these are processes of transformation, not termination. Earth's climate has swung between hothouse and icebox phases for billions of years, yet life persists, adapting to each new rhythm. Stars die in supernova, but their ashes seed new generations of planets. Even the hypothetical Big Crunch, a collapse of the universe into a singularity, isn't an end in most models. It's a reboot, a chance for new physics to emerge from the ashes. Science doesn't strip the cosmos of wonder, it deepens it. Where myths offer spectacle, research reveals symphonies, the gravitational waves from colliding black holes humming in the key of C-sharp, the fractal branching of galaxy clusters echoing snowflake patterns. The next time someone warns of an impending cosmic catastrophe, remember, the universe's true cycles aren't threats. They're invitations to look closer, to decode the rhythms that have guided everything from the first atoms to the rise of civilizations. And that's a story far more thrilling than any apocalypse. As we stand beneath the vast cosmic tapestry, one truth emerges with striking clarity. The universe speaks in rhythms, not randomness. From the subatomic flicker of quantum particles to the stately pirouette of galaxy clusters, cycles reveal themselves as nature's most profound language. Ancient sky watchers glimpsed this truth in the returning paths of planets, while modern astrophysicists chart it in the oscillations of spacetime itself. The spiral arms of distant galaxies, the heartbeat regularity of pulsars, even the mysterious fluctuations of dark energy, all whisper of a reality far more intricate than mere linear progression. This cyclical perspective transforms how we see our place in the cosmos. Rather than fleeting visitors in an indifferent universe, we're witnesses to patterns that stretch across eons, participants in a grand, unfolding rhythm. When you gaze at the night sky, you're not just seeing distant points of light, but the turning gears of a celestial mechanism so vast its full design still eludes us. Each discovery, from exoplanets locked in orbital resonance to the quantum echoes of possible past universes, adds another piece to this magnificent puzzle. The journey doesn't end here. With every new telescope probing deeper into space, every quantum experiment peeling back layers of reality, we edge closer to deciphering the universe's hidden cadence. Perhaps future breakthroughs will reveal cycles within cycles, like nested Russian dolls, or uncover entirely new periodicities that reshape our understanding of existence itself. One thing remains certain: the cosmos keeps time on scales both unimaginably vast and exquisitely minute, and we've only just begun to listen to its beat. What patterns will we discover next? Could dark matter hum in harmonic frequencies? Might black holes encode cyclical memories in their Hawking radiation? The questions multiply, but that's the thrill of exploration. Each answer unveils new mysteries. For now, we can marvel at how deeply this rhythmic reality resonates, from the Fibonacci spirals in sunflower seeds to the pulsing quasars at the edge of observable space. The universe may be the ultimate clockmaker, but we're the fortunate ones getting to watch the hands move. Your thoughts on these cosmic cycles? Share them below. Let's keep the conversation spinning like the galaxies themselves. And if you enjoyed this journey through time's grand patterns, be sure to subscribe for more explorations at the frontier of space and science. Until next time, keep looking up. The cosmos has countless rhythms left for us to discover.